Alright, let's take a look at notes 3.4. In this section we're going to be looking at the fundamental theorem of algebra and the linear factorization theorem. Okay, these sound kind of scary, but once we start doing examples it won't seem so much. The fundamental theorem of algebra must be pretty important. It says if a function has a polynomial of degree n, remember n is the exponent, where n is a number greater than 0, then the function has to have at least one 0 in the complex number system. Okay. As a reminder, the complex number system involves all real and imaginary numbers. So the 0 doesn't have to be real, it could be imaginary, but we have to have at least one. The linear factorization theorem says that if you have a polynomial of degree n, again where n is greater than 0, then that function n has precisely n linear factors. So if we have a third degree polynomial, then we're going to have 3 linear factors. Linear meaning that x's exponent is just 1. So here's a general factorization right here. So if this is a third degree polynomial, then we should be able to factor it into 3 linear factors, where c sub 1, c2, c sub n are complex numbers. And again, complex numbers could be either real or imaginary. Alright, so with that information, what are we going to be doing? We're going to be finding all the zeros of the function, and then deciding if there's a relationship between the number of those zeros and the number of real zeros and the number of x-intercepts of the graph, and then we're going to explain. To help us in our understanding of these questions that we're being asked to answer, I think the best thing is to take this function, and if they don't provide a graph for you, type it into your calculator and produce a graph. So just over here to the side, let's get a rough sketch. So if I pick up my calculator and type it in, I should see that I have a y-intercept at 0, negative 4. And as a reminder, if you're on the y-axis, if you have a y-intercept, then all x's are 0. You replace every x in this equation with 0. So these 3 terms will go basically down to 0, and I'll be left with negative 4. So if I didn't have a calculator, that's at least one easy point that I can identify by allowing every x to be 0. It's a cubic function, and it has a positive coefficient, so the behavior is falls left, rises right. And what happens is, let's see if I can draw this. The graph actually has a little bitty baby maximum right here, and then it kind of comes down, comes back up, and leaves the screen here. And on this end, since it has to fall to the left, okay, would look something like that. Alright, if you were to graph this, you would see that right here, this real 0, because I'm on the real number line, okay, appears to be 4. So for these couple of problems, you might want to first draw a graph if there's not a graph given, to have an understanding of the question. So if I look at this graph right here, I see that I have one real 0. Okay, and the most number of zeros I can have is 3, but I only have one real, so that must mean the other 2 zeros are going to be imaginary. Alright, so how do we find the real zeros without a calculator? Well, what we could do on this one is you can try and identify if you can factor this function. It looks like you can factor it by grouping. I think some of you guys like the box method. Either way will work. Pretty certain this will factor by grouping, but let's just revisit some skills that we've learned in the past few sections. If I didn't factor this by grouping, I could list all the possible rational zeros by taking the constant and dividing it by the leading coefficient, and I could get a whole list of possible rational zeros. Okay, that's a lot of work, but if I have this graph here to look at, it appears that 4 is a 0, so we're going to do synthetic division with 4. To avoid factoring, we're going to use synthetic division. To remind you, we're going to put all the coefficients in order on the first row, paying attention to if I have any missing terms that require a 0 placeholder. Alright, so let's do synthetic division. Bring down the 1, multiply by 4, add, the result is 0, multiply again, 0 is the product, add down, that's 1, the product is 4. I end up with 0 as a remainder, which means that 4 is a 0, so x minus 4 is a factor of this cubic. Come over here and remind yourself that these are the coefficients of the third degree problem, and when you do synthetic division, these coefficients right here are the coefficients of the second degree quotient. At this point, I can take these coefficients and build a quadratic equation. So it's x squared plus 0x plus 1, set it equal to 0. So at this point, I know there's certain methods that I could use to solve a quadratic equation. And since I'm down to a quadratic equation, I'm going to go ahead and see if I can solve this by one of those methods. I'm not going to use the quadratic formula. It doesn't factor. We might want to just extract the roots. So let's subtract a 1 from both sides. Let's bring in the even square root. And you notice we're going to have an imaginary result. Because it's an even root, we're going to bring out the absolute value of x. If we had an odd root that we brought in, we'd just bring out x, not the absolute value. This simplifies to I. Remove the absolute value, make the adjustment of positive negative I. So at this point, we have 3 zeros. And we should have 3 zeros because we have a cubic equation. The number of zeros will always match the degree of the polynomial. It just might be that there's a combination of real and imaginary. It might be all real zeros or it might be all imaginary zeros. It just depends upon the equation we're working with. That's supposed to be a colon. So our zeros are x equals 4, x equals negative I, and x equals positive I. I'm going to go ahead and factor into linear factors the cubic problem we're working with. We weren't asked, I don't think, to find the linear factorization, but that's going to help us with our later work. So the cubic polynomial up here can be factored into 3 linear factors, each of which of these zeros gives us a linear factor. So the 0 of x equals 4 is going to be equivalent to the factor, or it comes from the factor of x minus 4. Just think about subtracting 4 and putting it on the x side. Same thing here, but you're going to add a pi or a I. So x plus I, and this then for this 0, if I move the I over, I'd have x minus I. So this is the linear factorization of that cubic. Okay, so now going back to the question and what it asked us, find all the zeros of the function. We did that. Is there a relationship between the number of real zeros, in this case there was 1, and the number of x-intercepts of the graph? Remember, we're intercepting the real number line, so the x-intercepts, okay, are our real zeros. Yep, we have 1 real 0 and 1 x-intercept. So how do we respond to the question? Well, here we go. There is 1 real 0 and 1 x-intercept, so I'm just going to state they are the same. Meaning the number 1 is the same. 1 real 0, 1 x-intercept. Alright, let's look at example 2. Find all the zeros of the function. So I have to set f of x equal to 0 and either factor or maybe synthetic division. It's not a quadratic equation because the highest exponent is 4, so I'm going to have to rely on some other techniques for finding the zeros. First thing we're going to do is we're going to type this into our calculator, and when we do, I know quickly that the y-intercept is 4 because if x is 0 and x is 0 here, I'm going to have a y-intercept of 4. 0, 4 is the ordered pair. If you graph this on the calculator, it's going to almost look like it's the y equals x squared graph. The fourth degree function can really look like the quadratic graph if there's not a lot of other terms in here that contributes to hills and valleys or highs and lows or turning points. Anyway, it just looks like your basic y equals x squared graph. Okay. Going to the question, find all the zeros of the function. There'll be 4 of them. But if you notice right now, we have no x-intercepts. So what that means is there's no real zeros. They must all 4 be imaginary. If I don't cut through the real number line, then I have no x-intercepts and no real zeros. So that's the connection in these problems that we're trying to make. Alright, well let's find all 4 zeros, all 4 imaginary zeros. So set the equation, it's called a quartic equation, 4 equal to 0. I guess I could try and do synthetic division, okay, but however, if I try to do synthetic division, there's nothing on there's no x-intercept that suggests what starting place I should use. Like in this first example, the reason I chose 4 is because it appeared to be a real 0. Well, I have no real zeros, or at least it doesn't appear to be. So I can't really go to synthetic division, so my other option is, does this factor? Notice the exponent of 4, and then half of 4 is 2. Chances are this is going to factor into 2 binomials, where the first term of each binomial is x squared, so that the product gets you back to x to the 4th. Factors of 4 that add to 4. I think that's going to be 2 and 2. So this is a double factor. Alright, well, continue solving. Set each factor equal to 0. Since we have the same factor, we'll just solve one side and know what the other side's results would be. Subtract a 2. You see where this is going. Bring out the I. Square root of 2 won't simplify. Remove the absolute value. You have 2 imaginary solutions. And then over here, I'm just going to do a dash, 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 because the result will be the same. Notice that my imaginary zeros seem to be occurring in pairs, positive and negative. In the next video, we're going to see that those are called conjugate pairs. Alright, so let's state our zeros. So x equals negative I square root of 2. And let's just note to ourselves that this is a double 0. Comma. The other imaginary 0 is positive I square root of 2. And we'll also note that's a double 0 as well. Not real zeros, imaginary zeros. To help us with the next work that we have to do, let's go ahead and factor this into 4 linear factors. Remember, there has to be 4 distinct linear factors. So from these zeros right here, if I were to add I squared root of 2 to the other side, then the factor it comes from is x plus I squared root of 2. Well, if I'm writing out the factorization, then I need to write out both of them, because I need to clearly see 4 parentheses. Hopefully you see over here that this imaginary 0, when brought to the other side, would come from the factor x minus square root of 2, occurring twice. All right, so this is actually an extra step according to the instructions of what we're supposed to do. But let's go ahead now and answer the question. Okay. There are no real zeros. None of these answers up here were real. And there are no x-intercepts on the graph. All right, and to respond to the question, they are the same, meaning that 0 is the same as 0. 0 real zeros and 0 x-intercepts. So just write down they are the same. All right, so in the next video, we're going to continue our work with these two topics of the fundamental theorem of algebra and the linear factorization theorem.